In this lecture, we're going to look at the univariate, bivariate, and multivariate normal distributions. Structural equation models are based on an assumption that the responses have a multivariate normal distribution. In addition, in hierarchical linear models, the random effects and the model error term are assumed to be normally distributed. So it's going to be helpful for us to be familiar with these families of distributions, the parameters in each family, and procedures for estimating the parameters for each type of normal distribution. We will look at the form of the PDF, the probability density function, for each of these families of distributions and identify their various parameters. Finally, we'll look at how to derive maximum likelihood estimators for these parameters and how to obtain unbiased estimators of the parameters by adjusting those maximum likelihood estimators that happen to be biased. So here's a review of what we'll be looking at in this video. We'll be looking at the normal or Gaussian distributions. We'll look at the univariate normal distribution. Then we'll generalize a bit and look at the bivariate normal distribution. And then finally, we'll look at the general multivariate normal distribution. We'll look at how to estimate the parameters of the univariate normal distribution using maximum likelihood. And then finally, we'll look at how to estimate the parameters of the multivariate normal distribution, which includes the bivariate normal distribution, again, by using the principle of maximum likelihood. So let's look at the normal distributions, and in particular, the PDFs of the normal distributions, and identify their parameters. So we'll start off by looking at the univariate normal distribution. So let X be a continuous random variable with probability density function, or PDF, given by the following expression. F of X equal to 1 over the square root of 2 times pi times the quantity sigma squared sub x, all of that times the exponential function evaluated at -1/2 times the square of the difference between the function argument x and a quantity mu sub x, and then we divide that squared difference by this quantity sigma squared sub x. Now you'll recall that the exponential function evaluated at an argument is defined to be, or is equal to, the real number e raised to a power equal to the argument at which we're evaluating the exponential function. And so you can see both types of notation here. Now, when a continuous random variable x has a probability density function equal to this kind of expression, the random variable x is said to have a univariate normal distribution with mean mu sub x and variance sigma squared sub x. Now, we don't want to have to write out the PDF whenever we want to express this type of idea, and so we have a nice handy notation here, or abbreviation, that we can use to do this. And so we would write this as the random variable x, and then tilde, which is an abbreviation for is distributed as, and then we have n for the normal distribution, and then we list the parameters after that inside parentheses. And so this would be read, the random variable x is distributed according to a normal distribution with a mean of mu and a variance of sigma squared sub x. Now, there are an infinite number of univariate normal distributions. There is a normal distribution for each combination of the mean mu and variance sigma squared. Now, mu can be any real number. Sigma squared, on the other hand, has to be a positive real number. And so when you combine the two, you can see then that there are an infinite number of normal distributions, and each normal distribution is uniquely identified or uniquely specified once we specify the mean and the variance of that distribution. Now, there is one univariate normal distribution that has a special name, and special usage, this is the normal distribution that has a mean of 0 and a variance of 1. Now you'll recall that the standard deviation of a distribution is equal to the square root of the variance. And so if the variance is equal to 1, the standard deviation is equal to 1 as well, obviously because the square root of 1 is 1. So the normal distribution with a mean of 0 and a variance of 1, or standard deviation of 1, is a special normal distribution. This is the distribution that we base tables on, and this distribution is called the standard normal distribution. So you'll recall that in your previous courses, statistics courses, you used the standard normal table when you were looking up critical points for hypothesis tests that are based on the normal distribution, and also in looking up interval coefficients when constructing confidence intervals for a population mean, for example, when the procedure is based on the normal. So the normal distribution with a mean of 0 and standard deviation of 1 is called the standard normal distribution. And we typically denote a standard normal random variable by an uppercase Z. And so using that notation, we would say that Z and then tilde is distributed according to a normal distribution with a mean of 0 and a variance of 1. Now, the PDF of the standard normal distribution is obtained from the expression for the PDF on the previous slide by plugging in 0 for mu and 1 for sigma squared. And so when we do that, we see that the PDF of the standard normal distribution is given by f at z is equal to 1 over the square root of 2 times pi times the exponential function evaluated at negative 1/2 times z squared. Now, every normal distribution is unimodal. It has a single hump, and it's symmetric about the vertical line going through its mean. And so the normal distribution has that familiar bell-shaped curve. Now, this slide shows 3 examples of normal PDFs. Each of these distributions has a mean of 0, but they have different values for their standard deviation. And so the red curve, that is the PDF of a standard normal distribution, because that distribution has a mean of 0 and a standard deviation of 1. The blue curve is the PDF for the normal distribution with a mean of 0 and a standard deviation of 2. And then finally, the green curve is the PDF of a normal distribution with a mean of 0 and a standard deviation of 4. And so you can see that normal distributions with the same mean are centered at the same spot, but the way they're going to differ is based on how spread out they are, and that characteristic is controlled by the standard deviation. And you can see that the larger the standard deviation, the more spread out the PDF is. But let me also point out, and this will be familiar to you from your previous statistics courses, but the area under each one of those curves is equal to 1. And this is because, in general, for any distribution, the area under the curve of the PDF for that distribution is always equal to 1. Now, this slide shows examples of 3 normal PDFs. Each one has a variance equal to 1, and therefore the standard deviation is equal to 1 as well, but they have different means. So the blue curve in this particular slide is the PDF for the standard normal distribution, because it has a mean of 0 and a variance of 1, and therefore a standard deviation of 1. The red curve is the PDF for the normal distribution, with a mean of -4, and again, a variance of 1, and therefore a standard deviation of 1. And then finally, the green curve is the PDF of the normal distribution with a mean of +4 and a variance of 1, and therefore a standard deviation of 1. And so you can see that in this graph, the location of where the PDF is centered depends on the mean. And so as you increase the mean, the location of the center point for the distribution moves to the right. If you decrease the mean, then the distribution is going to shift to the left. And so again, just as a reminder, you've worked with standard normal distributions a lot in your previous statistics courses, not only the standard normal, but many normal distributions. But you've used the standard normal distribution in particular quite a bit because, again, this is the normal distribution that normal tables are based on. And so again, in many books, the standard normal table is a right-tailed table, as this one is, which means that the table is giving you right-tailed areas. Next, let's look at the bivariate normal distribution. Let x1 and x2 be continuous random variables with a joint PDF, lowercase f, given by the following expression. So this is a bivariate PDF, and so it has two arguments. We'll label them x1 and x2, corresponding to the random variables x1 and x2. And so f of x1 and x2 is equal to 1 over 2 times pi times 1 over the square root of sigma 1 squared times sigma 2 squared times 1 minus rho squared. All of that times the exponential function evaluated at -1/2 times a quantity q, where q is this rather complex expression at the bottom of the slide. So q is equal to 1 over 1 minus rho squared times the large quantity, the square of the difference between the argument x1 and mu1, that divided by sigma 1 squared, minus 2 times rho times the quantity x1 minus mu1 over the square root of sigma 1 squared times x2 minus mu2 divided by the square root of sigma 2 squared, and then plus the square of the difference between argument x2 and mu2, that square difference divided by sigma 2 squared. So when two continuous random variables, x1 and x2, have this joint PDF, they are said to have a bivariate normal distribution with parameters given by the following: mu1, mu2, sigma 1 squared, sigma 2 squared, and rho. So there are 5 parameters in this PDF. If we look back at the slide, you can see that. You can see we have sigma 1 squared and sigma 2 squared, as well as rho squared in the denominator in that second component on that first line. And then in the quantity q, we have not only the sigma 1 squared, sigma 2 squared, and rho values, but we have mu 1 and mu 2 as well. Now mu 1 is the expected value of x1. Similarly, mu2 is the expected value of x2, or in other words, the mean of the random variable x2. Sigma 1 squared is the variance of x1. Sigma 2 squared is the variance of x2. And then rho is the correlation between x1 and x2. Now note that the PDF is completely specified by these 5 parameters: the 2 means, the 2 variances, and the correlation between the 2 random variables. Now we could express the PDF in terms of the covariance instead of the correlation. We would just need to rewrite it using the relationship between the correlation, the covariance, and the variances of the 2 random variables. And so I would recommend that you look to see how you could rewrite this PDF using the covariance instead of the correlation. So the PDF is fairly complex. Let's look at another way of representing this PDF that kind of hides some of the details. And so this is going to be the matrix representation of the distributional parameters that we will then incorporate into another equivalent expression for the PDF. And so let's let bold x be a 2x1 vector containing the function arguments x1 and x2. We'll let mu sub bold x be a 2x1 vector containing the means of random variables x1 and x2. So it has mu1 in the 1,1 entry and mu2 in the 2,1 entry. And then we'll let bold sigma sub bold x be a 2x2 matrix that contains sigma 1 squared in the 1,1 entry, sigma 2 squared in the 2,2 entry, and then in the entries in position row 1, column 2, and also row 2, column 1, we'll have the quantities sigma 1 times sigma 2 times rho. Now note that the quantity that I just discussed, sigma 1 times sigma 2 times rho, that is the covariance of x1 and x2. So we are taking these parameters and we are packaging them in terms of vectors and matrices. Now note that the determinant of the covariance matrix cap sig sub bold x is equal to sigma 1 squared times sigma 2 squared times 1 minus rho squared. And so with that, we can write the inverse of this 2x2 matrix as 1 over 1 minus rho squared times the 2x2 matrix with entries 1 over sigma 1 squared in the 1,1 entry, 1 over sigma 2 squared in the 2,2 entry, and then in the entries in row 1, column 2, and also row 2, column 1, we have the quantity negative rho over sigma 1 times sigma 2. So that is the inverse of the covariance matrix, cap sig sub cap x. And you'll notice that the quantity q can be expressed in terms of the x vector, the mu vector, and the inverse of cap sig in the following way. Q is equal to the transpose of x minus mu sub x pre-multiplied against the inverse of this matrix cap sig, and then post-multiply that by x minus mu sub x. So if you're really interested in this, you can work this out by doing the various matrix multiplications here, and you're going to find that the expression that results is equal to Q as shown on the bottom of this slide. Now with all that, the joint PDF of the bivariate random vector bold x, which is the 2x1 vector containing the random variables x1 and x2, it can be written in the following way. So f of x1, x2 is equal to 1 over 2 times pi times the square root of the determinant of cap sig sub x times the quantity, the exponential function evaluated at negative 1/2, times this expression where we have the transpose of the difference between the argument x vector and the mu vector, pre-multiplied against the inverse of the sigma matrix, which is then post-multiplied by x minus mu sub x. So this is a little bit simpler than the other expression we had that was expressed in terms of scalar quantities. And so we see that the version written in terms of vectors and matrices is much more, or at least a bit more compact than the version that's expressed in terms of the scalars. In addition, since this representation automatically incorporates the dimensionality of the distribution, it would appear that this type of representation would be easily scalable to dimensions greater than p equal to 2. And so with that in mind, let's look at the multivariate normal distribution. So let bold X be a p by 1 vector consisting of p continuous random variables, x1, x2, and so forth up to x sub p, with joint PDF given by the following expression. The function f evaluated at the argument vector lowercase x, and so this is equivalent to the function f evaluated at x1, x2, and so forth up to x sub p, being equal to 1 over 2 times pi, that quantity raised to the power p over 2, times the square root of the determinant of cap sig, that times the exponential function evaluated at -1/2, times the transpose of x minus mu sub x, pre-multiplied against the inverse of cap sig sub x, which is then post-multiplied again by x minus mu sub x. Now, this can also be written in the following way. 2 times pi raised to the negative p over 2 power times the square root of the determinant of the inverse of cap sig sub x, and then multiply that against the exponential function, again evaluated at -1/2, times the transpose of x minus mu sub x, which is pre-multiplied against the inverse of cap sig sub x, which is then post-multiplied against x minus mu sub x. And here the x vector, lowercase x vector, x1 through x sub p, is a point in a p-dimensional Euclidean space, which we denote by cap r raised to a p. In addition, mu sub x in that expression is the p by 1 vector containing the values or the quantities mu1, mu2, and so forth down to mu sub p. And those quantities are the expected values of the random variables. So mu1 is equal to the expected value of x1, mu2 is the expected value of x2, and so forth, down to the final quantity, mu sub p, which is equal to the expected value of x sub p. Now, we can also represent this p by 1 vector of expected values as the expected value of the p by 1 vector containing the random variables, which could then also be represented more succinctly as the expected value of the p by 1 vector bold X. And then finally, cap sig sub x, in this context, is a p by p positive definite matrix given by the following. And so cap sig sub x is the p by p matrix. It's a square matrix. And the ij entry of this matrix is the covariance of x sub I and x sub j. So for example, we have on the first row sigma 1, 1, sigma 1, 2, and so forth up to sigma 1 sub p. So in that case, sigma 1, 2 is the covariance of x1 and x2. Sigma 1p is the covariance of x1 and xp. If we look at that first column, it contains the values sigma 1, 1, sigma 2, 1, and so forth down to sigma p sub 1. And so in that column, sigma 2, 1 is the covariance of x2 and x1, and continuing on down, x sub p1 is the covariance between xp and x1. Now looking down the diagonal, we have entries sigma 1, 1, sigma 2, 2, and so forth down to sigma pp. Well, sigma 1, 1 is the covariance of x1 with itself, and you'll recall that that is the variance of x1. Similarly, sigma 2, 2 is the covariance of x2 with itself, and so that is the variance of x2, and so forth down to the last entry, sigma pp. This is the covariance of xp with itself, which is the variance of x sub p. And so the p by p matrix, cap sig sub x, contains the variances of the random variables x1 through xp down the diagonal, and the off-diagonal elements contain the covariances between the various random variables. Now note that the covariance matrix cap sig sub x is symmetric. And this is because sigma ij, which is equal to the covariance of x sub I and x sub j, that is the same as the covariance of x sub j and x sub I. And this is because, as you'll recall, one of the properties of the covariance function is that the order of the arguments is irrelevant. Well, that second covariance quantity, the covariance of x sub j and x sub I, that is sigma ji. And so we see here that sigma ij is equal to sigma ji, and so that implies that the matrix cap sig sub x is symmetric. The PDF given above is that of the p-dimensional multivariate normal distribution with mean vector mu sub x and covariance matrix cap sig sub x. The random variable x is said to have a multivariate normal distribution with mean vector mu sub x and covariance matrix cap sig sub x. And we denote this, we abbreviate this in the following way. So bold x, which is a p by 1 random vector of random variables, is distributed according to a multivariate normal distribution of rank p, of dimension p, with mean vector given by mu sub x and covariance matrix given by cap sig sub x. So as we've seen, the various normal distributions, the univariate normal distribution, the bivariate normal distribution, and the general multivariate normal distribution have a number of parameters associated with those distributions. Now, theoretical constructs and research questions are typically expressed in terms of these kinds of parameters. Because these parameters are unknown, we have to make inferences about them, and the first step in that process is to estimate their values. And so that's what we're going to do in the next section. So let's first look at the univariate normal distribution with its two parameters, the mean and the variance, and let's see how to come up with estimators for those parameters. So let x1, x2, and so forth up to x sub n be a random sample of size n from the normal distribution with mean mu and variance sigma squared. Now for each I going from 1 to n, the marginal PDF of x sub I is given by this expression that we saw several slides ago. And since each random variable has its own marginal PDF, we're going to subscript the PDFs with the index I. So f sub I with argument x sub I and parameters mu and sigma squared is given by the following expression. 1 over the square root of 2 times pi times sigma squared times the exponential function evaluated at negative 1/2 times the quantity, the square of the difference between x sub I and the mean mu divided by sigma squared. Now, because the random variables x1, x2, and so forth up to x sub n constitute a random sample, you'll recall that one implication of the term random sample is that the random variables comprising that sample are stochastically independent. The other implication is that they are identically distributed. So a random sample is a sample in which the random variables are IID, independent and identically distributed. Now, because the random variables x1 through xn are stochastically independent by virtue of being a random sample, their joint PDF is equal to the product of their marginal PDFs. All right, so if we denote the joint PDF by lowercase f without a subscript, then f evaluated at x1 through x sub n where the parameters associated with this distribution are again mu and sigma squared, the underlying mean and variance of this normal distribution. That joint PDF can be expressed as the product of the marginal PDFs. So the product, I going from 1 to n, of f sub I, evaluated at x sub I, colon or semicolon, and then the parameters mu and sigma squared. And so when we evaluate that product, we get 2 times pi raised to the negative n over 2 power times sigma squared, also raised to the negative n over 2 power. And then that expression multiplied against the exponential function evaluated at negative 1/2 times the sum, I going from 1 to n, of x sub I minus mu quantity squared over sigma squared. So this is the joint PDF of the random variables in our random sample. The likelihood function is the joint PDF, but considered as a function not of the argument variables x1 through xn, but rather a function of the parameters mu and sigma squared, and we consider the values of x1 through xn to be fixed. So we can then consider this as a function of the two parameters mu and sigma squared. The likelihood function will be denoted by uppercase L, evaluated at mu and sigma squared. And so it's equal to this same expression that we had for the joint PDF. Now, one important thing to keep in mind is the parameter space for the parameter associated with this distribution. We're going to denote the parameter space by capital Omega, and it's equal to the set of ordered pairs mu comma sigma squared, where mu can be any real number, and so we denote the real number line by uppercase R, so an uppercase script R. And in addition, sigma squared can be any real number that is greater than 0. So the collection of all such ordered pairs or points in a two-dimensional Euclidean space constitutes the parameter space for the normal distribution. Now, if there exists a point in the parameter space, and we're going to denote this point by the ordered pair mu tilde and sigma squared tilde. So if there exists such a point in the parameter space such that the likelihood function cap L evaluated at that point, mu tilde comma sigma squared tilde, is greater than or equal to the likelihood function cap L evaluated at mu comma sigma squared for all such points, mu comma sigma squared in the parameter space, then this point, mu tilde comma sigma squared tilde, is called a maximum likelihood estimator, or MLE, of the true parameter point, mu comma sigma squared. In other words, the maximum likelihood estimators of mu and sigma squared are the values of these parameters in the parameter space at which the likelihood function is maximized. So to find the maximum likelihood estimators of the parameters, we've got to find values of the parameters in the parameter space which maximize the likelihood function cap L. Now the natural log of the likelihood function, which is called the log likelihood, is given by the following expression. We denote it by lowercase l, evaluated again at mu and sigma squared, and it's equal to negative n over 2 times the natural log of 2 times pi minus n over 2 times the natural log of sigma squared minus 1/2 times the sum, I goes from 1 to n, of x sub I minus mu quantity squared divided by sigma squared. So this is the expression that we get if we calculate the natural log of the likelihood function cap L. It's the log likelihood, and we denote it by lowercase script l. Now, since the logarithm is a strictly increasing function, the values of mu and sigma squared that maximize the log likelihood will also maximize the likelihood function itself. In addition, it turns out to be easier to work with the log likelihood function than with the likelihood function itself, because if you look in the expression for the log likelihood, we're dealing with sums, whereas in the likelihood function itself, we're dealing with products. So because it's easier to work with the log likelihood than it is the likelihood function itself, we usually maximize the likelihood function indirectly by maximizing the log likelihood function instead. And again, because the logarithm function is an increasing function, if the values that maximize the log likelihood function are the same values that will maximize the likelihood function. Now, one way to find the MLEs, the maximum likelihood estimators of mu and sigma squared, is to differentiate the log likelihood function with respect to mu and sigma squared individually, set those two derivatives equal to 0, and then solve the resulting of the system of equations for mu and sigma squared. Now, the partial derivative with respect to mu is equal to this expression on the right-hand side, the sum, I going from 1 to n, of x sub I minus mu over sigma squared. The partial derivative with respect to sigma squared is equal to negative n over 2 times sigma squared plus 1 over 2 times the square of sigma squared times the sum I goes from 1 to n of x sub I minus mu quantity squared. Setting these derivatives equal to 0 and denoting the MLEs by mu tilde and sigma squared tilde, we get the following system of equations. The first equation being the sum I going from 1 to n of x sub I minus mu tilde over sigma squared tilde being equal to 0. And the second equation in the system is negative n over 2 times sigma tilde squared plus 1 over 2 times the square of sigma tilde squared, that quantity times the sum I going from 1 to n of x sub I minus mu tilde quantity squared. And again, we set that equal to 0, and that gives us the second equation in the system. Now, this system of equations gives constraints that the MLEs, mu tilde and sigma tilde squared, must satisfy. Solving that system for mu tilde and sigma tilde squared gives the maximum likelihood estimators of mu and sigma squared. And so the maximum likelihood estimator of mu is given by mu tilde equal to 1 over n times the sum I going from 1 to n of x sub I. And you'll recognize that that is the sample mean of the x's. The MLE of sigma squared is sigma tilde squared, which is equal to 1 over n times the sum I going from 1 to n of x sub I minus mu tilde. That says hat there, but for right now that should be a tilde. So the sum I going from 1 to n of x sub I minus mu tilde quantity squared. Now you'll recognize that sigma tilde squared is a version of the sample variance that has n in the denominator rather than n minus 1. Now it can be shown that the expected value of mu tilde, the MLE of mu, is equal to mu. And this implies that mu tilde is an unbiased estimator of mu. You'll recall that the definition of a random variable or estimator being unbiased is that its expected value is equal to the quantity we're using it to estimate. And so because the expected value of mu tilde is equal to mu, that implies then that mu tilde is an unbiased estimator of mu. Now, since mu tilde is an unbiased estimate of mu, it's standard to denote it by mu tilde. And so that's why on the previous slide, I had the mu hat. And so you can see there that I kind of jumped the gun on that notation, and I used mu hat in this slide. Now, on the other hand, the expected value of sigma tilde squared is equal to n minus 1 times sigma squared over n. Another way to write that would be n minus 1 over n times sigma squared, and that is strictly less than sigma squared. So the expected value of sigma tilde squared is not equal to sigma squared. It's a little bit less than sigma squared. And because of that, sigma tilde squared is biased as an estimator of sigma squared. Because of this, we usually use the unbiased version of the sample variance as an estimator of sigma squared. The unbiased version is the usual sample variance, which we'll denote here by sigma hat squared, which will be n over n minus 1 times sigma tilde squared, and that is equal to 1 over n minus 1 times the sum I going from 1 to n of x sub I minus mu hat sigma squared. And you'll recognize that last expression as being the usual sample variance that we use, and it's the version of the sample variance that you used in your first methods courses. And so sigma hat squared is usually the estimator that we'll use to estimate sigma squared because it is unbiased as an estimator of sigma squared. Next, let's look at how to estimate the parameters of the general multivariate normal distribution. So let bold x1, bold x2, and so forth up to bold x sub n be a random sample of p by 1 vectors from the multivariate normal distribution with mean vector mu sub x and covariance matrix cap sig sub x of rank p. For each I, going from 1 up to n, the joint PDF of the components of the ith random vector x sub I is given by the following expression. So f sub I, evaluated at x sub I, with parameters the mean vector mu sub x and covariance matrix cap sig sub x, this is equal to the expression 1 over 2 times pi raised to the p over 2 power times the square root of the determinant of the covariance matrix cap sig sub x. That quantity times the exponential function evaluated at negative 1 over 2 times this quadratic form, the transpose of x sub I minus mu sub x, pre-multiplied against the inverse of the covariance matrix, which is then post-multiplied by x sub I minus mu. Now, since bold x1, bold x2, and so forth up to bold x sub n is a random sample, the random vectors are stochastically independent of one another. The joint PDF of these n random vectors comprising the random sample is therefore equal to the product of their marginal PDFs, so that the joint PDF of this random sample of p by 1 vectors is given by f, evaluated at bold x1 through bold xn as arguments, with mu sub x as the mean vector and cap sig sub x as the covariance matrix. That is equal to the product of the individual PDFs. And so this turns out to be 2 times pi raised to the negative n times p over 2 power times the determinant of the inverse of the covariance matrix, that expression raised to the n over 2 power, and all of that times the exponential function evaluated at negative 1/2 times the sum I going from 1 to n of these quadratic form expressions, the transpose of x sub I minus mu sub x, pre-multiplied against the inverse of the covariance matrix, which is then post-multiplied by the difference between x sub I and the mean vector mu sub x. Now, the likelihood function is equal to this joint PDF, but we consider it again as a function of the mean vector mu sub x and the covariance matrix cap sig sub x, with x1 through x sub n being fixed values of the data. The likelihood function, as it was in the one-dimensional case is denoted by uppercase L. It's a function of the parameters, all right, which would be mu sub x and cap sig sub x, and it's therefore given by this expression. So cap L evaluated at mu sub x and cap sig sub x is just equal to the joint PDF of the data evaluated at x1 through xn, with mu sub x and cap sig sub x being the mean vector and covariance matrix, respectively. Now the parameter space, which we will again denote by uppercase omega, is the set of ordered pairs. But now the ordered pair here is a little bit more complicated because the first coordinate, the first entry in that ordered pair, is the mean vector, the p by 1 mean vector, and the second entry, the second coordinate, is a covariance matrix. It's a p by p matrix. And so the entries in that ordered pair, mu sub x, can range throughout all of p-dimensional Euclidean space. The second entry, cap sig sub x, has got to be a p by p positive definite matrix. And so the set of all such ordered pairs that satisfy those two requirements constitutes the parameter space for the multivariate normal distribution of dimension p. Now, if there exists a point in the parameter space, and we will denote that point as the ordered pair mu tilde sub x and cap sig tilde sub x. So if there exists a point in the parameter space such that the likelihood function evaluated at that point is greater than or equal to the likelihood function evaluated at any other point in the parameter space, then this point, mu tilde sub x, comma cap sigma tilde sub x, is called a maximum likelihood estimator, again MLE, of the true parameter point mu sub x, comma sigma sub x. In other words, the maximum likelihood estimator of mu sub x and cap sig sub x is the point in the parameter space at which the likelihood function cap L is maximized. To find the maximum likelihood estimators of the parameters, the mean vector and the covariance matrix, we've got to find a point in the parameter space at which the likelihood function is maximized. Now again, since the logarithm function is strictly increasing, the values of the mean vector mu sub x and covariance matrix cap sig sub x that maximize the log likelihood function also maximize the likelihood. And since, again, it's easier to work with the log likelihood because it involves just sums, rather than the likelihood function itself, which involves products, we usually maximize the log likelihood function. And then when we've done that, we know that we have the maximum likelihood estimators, the values for the parameters that would maximize the likelihood function as well. Now, for this situation, the log likelihood function, which again is obtained by taking the natural log of the likelihood function, is denoted by lowercase script l, and it turns out to be that it's equal to negative np over 2 times the natural log of 2 pi plus n over 2 times the natural log of the determinant of the inverse of the covariance matrix minus 1/2 times the sum, I going from 1 to n, of these quadratic forms, the transpose of x sub I minus mu sub x, pre-multiplied against the inverse of the covariance matrix, which is then again post-multiplied by x sub I minus mu sub x. One way to find the maximum likelihood estimators is to differentiate the log likelihood with respect to each of the mean vector mu sub x and the covariance matrix cap sig sub x, set the derivatives equal to the zero matrix of appropriate dimension, depending upon whether we're differentiating with respect to the mean vector or the covariance matrix, and then solve the resulting system of equations for mu sub x and cap sig sub x. The calculations in the multivariate case are a bit more complicated than they were in the univariate case, but the overall idea is the same, and so we're not going to go through those calculations here. But when we do that, we're able to solve the resulting system of equations and come up with nice formulas for the maximum likelihood estimators of mu sub x and cap sig sub x. Doing that, the formulas for the maximum likelihood estimators are given on the next slide. And so the maximum likelihood estimator of mu sub x, which is denoted by mu tilde sub x, is equal to 1 over n times the sum, I going from 1 to n, of the data vectors x sub I. The maximum likelihood estimator of sigma sub x is sigma tilde sub x equal to 1 over n times the sum, I going from 1 to n, of the quantity x sub I minus mu hat sub x. And again, that mu hat, well, I'm getting a little ahead of myself. Okay, that's going to be the same as mu tilde. All right, that's the MLE of mu sub x. So x sub I minus mu hat sub x times the transpose of that same difference. So the transpose of x sub I minus mu hat sub x. Now it turns out, if you do the calculations, that that is equivalent to 1 over n times the sum, I going from 1 to n, of x sub I times the transpose of x sub I, and then minus mu hat sub x times the transpose of mu hat sub x. Now it can be shown that the maximum likelihood estimator, mu tilde sub x, is an unbiased estimator of the mean vector mu sub x. And so because of that, as in the univariate case, it's standard to denote this unbiased estimator by mu hat sub x. And again, just like I did in the univariate case, I jumped the gun on this notation and I used mu hat sub x on the previous slide. So I hope that doesn't confuse you. Now, on the other hand, it can be shown that sigma tilde sub x is biased as an estimator of the covariance matrix cap sig sub x. In particular, the quantities in the maximum likelihood estimator tend to be attenuated towards 0. And so because of this, we can come up with a bias corrected version, and we're going to denote that bias corrected version by sigma hat sub x. Now, expressed in terms of sigma tilde sub x, it would be equal to n over n minus 1 times sigma tilde sub x, where again, sigma tilde sub x is the MLE of sigma sub x. And that is equal to 1 over n minus 1 times this sum that we saw on the previous slide. So that bias corrected version of the covariance matrix is usually the one that's used to estimate the covariance matrix. It's called the sample covariance matrix, and we use it because it's unbiased as an estimator of sigma sub x. Now, note that the bias corrected version, the usual sample variance, sigma hat sub x, can be written in the algebraically equivalent form shown here. So sigma hat sub x equal to 1 over n minus 1 times the quantity, where we have the sum I going from 1 to n, of x sub I times x sub I transpose minus n times mu hat sub x times the transpose of mu hat sub x. And so it's basically the same expression we had a couple slides ago, but instead of dividing by n, we're dividing by n minus 1. Now, the formulas given above for mu hat sub x and cap sig sub x, the unbiased estimators of mu sub x and cap sig sub x, respectively, are matrix expressions that follow from the derivations based on the maximum likelihood principle. If one has access to matrix manipulation software, then these formulas can be easily used for calculation. But if calculations must be done by hand, for example with a hand calculator, these formulas are not terribly useful unless, of course, your calculator has matrix functionality. Now, the good news is that both mu hat sub x and cap sig hat sub x can be constructed by calculating their individual elements separately And this is helpful when calculations must be done by hand. So let's take a look at this. So calculating the individual elements of mu hat sub x. And so mu hat sub x, we saw this is equal to 1 over n times the sum I going from 1 to n of the data vectors x sub I. And so you can see here that this is just the n by 1 vector of, I'm sorry, this says n, it should be p. We should have x1, x bar 1, x bar 2, and so forth down to x bar sub p. So this is a p by 1 vector containing the sample means for the p variables that we're measuring. So in words, the individual elements of mu hat sub x are the individual sample means of the p individual variables. So I'll correct that in the notes, but just make a note as you think of, or as you're watching this, that there's a little typo right there at the end. The individual elements of sigma hat sub x, the unbiased estimator of the covariance matrix, are shown here. So this shows the notation of the entries in that p by p matrix. The formulas for these various quantities are given on the following slide. And so the ith diagonal element of sigma hat sub x is given by the following. Sigma hat sub I, which is the estimated covariance of x sub I with itself. And you know that that is the estimated variance of x sub I. So I see here I've got another little typo. I should have a hat on that variance. Okay, so sigma hat sub I is the estimated variance of var hat sub xi, and that is equal to 1 over n minus 1 times the sum r going from 1 to n of x sub r sub I minus x sub I bar quantity squared. And so this is just the formula for the sample variance of the ith response variable. The off-diagonal element in row I and column J of cap sig hat sub x is given by the formula sigma hat sub ij. Again, this is the estimated covariance of x sub I and x sub j. This is equal to 1 over n minus 1 times the sum r going from 1 to n of x sub ri minus x sub I bar times the quantity x sub rj minus x bar sub j. And that is equal to this computational formula, 1 over n minus 1 times the sum r going from 1 to n of x sub ri times x sub rj minus 1 over n times the sum of the x sub ri's and the sum of the x sub rj. So in other words, the sum of the x sub I values and the sum of the x sub j values. So this is the sample covariance of the ith and jth response variables. And so using these formulas, the estimators mu hat sub x and sigma hat sub x can be piecewise constructed by first calculating their individual components and then putting these components together in the appropriate way. So that's what I wanted to show you in this lecture video. I'll see you in the next lecture video.